Alright, in this video we're going to be looking at the Serial Peripheral Interface, or SPI port, on our microcontroller. Basically, we have a number of pins on our micro, and they have particular names associated with the SPI port. SCK, MOSI, MISO, and SS, or chip select, or sometimes chip enable, noting that those little bars over the top there are for active low pins. Alright, so this is our micro. SPI is a serial synchronous communications strategy. Here's our device. This guy is called the slave, and our normally microcontroller is called the master. Between these we have the 4 lines connected. Now note the direction of the arrows. Alright, SCK is our clock source, so that's our clock line. MOSI is master out, slave in, hence the arrow going in. MISO is master in, slave out, hence the arrow going into the microcontroller. And slave select, or chip select, or as I said sometimes, chip enable, are often names used for this line. Right, so that's just a digital control line, which could go high or it could go low. Doesn't really matter, it just has to stay in a particular state. Alright, so that's basically the setup of SPI. Nice things about it is this clock can go up to several megahertz, so we can clock data really quickly between our master and our slave. Right, so we have fast data transfer. We have full duplex operation, because we have both a transmit and receive line effectively. We also have the opportunity to have multiple slaves, so there's nothing stopping you with SPI having multiple slaves and taking out in parallel each of these lines to slave 2, for example, and having a new slave select or chip select line associated with it. The only problem with doing that is that for every slave device you add, you're going to need another chip select or slave select chip enabled line from your microcontroller, so you can end up having a lot of I/O lines. It's best if you're doing that to use a decoder. So multiple slaves is fine with SPI, but 1 times chip select per slave can give a little bit of problems in terms of I/O usage. But the other thing is, it is using SPI is easy, almost as easy as a UART or a RS-232 port. So it's a really nice interface to have to use, and one that I much prefer over I2C. So let's have a look how it works. We have our SCK, our clock line. We'll have our MOSI, master out, and our MISO line. Alright, at some point, and our slave select or chip select line. At some point, our slave select line, this is 0 and this is, let's say, logic 1, high voltage, we're going to pull that low. Alright, and if it's slave select, then it's probably going to be active low, so that's why we're pulling it low. So we pull this line low. This point means we want to start communicating with our slave device. Alright, so this is this line here that I'm just talking about here, connected to our slave device. SCK is our clock up here. When that happens, it's sometime after that slave select line goes down, not immediately at the same time, we start generating a clock signal. Now that clock signal might be idle low, as I show here, or it might be idle high, so it's normally high pulled low. We'll show you that later on. But when we start clocking through information, out of our master we can start transferring bits. Alright, so let's say, for argument's sake, that's 8 bits that we've clocked out, and that's generally how SPI works, through an 8-bit interface, depending on the microcontroller. In fact, we might do that in just a slightly different color. So this bit here is 8 bits. Alright, so just pretend I've got 8 clock cycles and 8 bits of information come out there. During this time, our meso line could be looking for reading an input, depending on how it's set up. But let's just say for now, forget that it's looking for any input coming in. We're only interested in sending out some information. Alright, so we sent some information. There'll be a small delay here, perhaps before the next bit of information is sent or received. But most importantly, what has to happen now is that even though I have sent effectively OXOO here, now because the slave device has received an instruction here, so this is, let's say, an instruction or a command that we want it to perform, it now sends back some information. So this bit here is our received instruction. Once again, this whole bit is 8 bits. And at the end, we bring the chip select line back high again, and our communication is finished. Now, let's see this again, because it's very easy to miss. In this data transfer, which I showed you here, I have read 1 byte from the slave, but I've sent 2 bytes. And this is the gotcha with SPI that a lot of people miss. In the first frame of data I send, this guy here, and this is our second one here, in this first frame I send the instruction. Alright, now this could be the address of a register that I want to read, it could be the address of a register I want to write, it could be a command for the slave, turn on something, read something, do something, alright, but I've sent some information here. And what happens in reality is that every time I send something, so every time you send data, you also receive data. Alright, that's fundamental to the way SPI works. So I'm actually, while it looks like I'm only sending data here, I'm actually also at the same time receiving a byte. As it turns out, because we haven't sent anything previously, this is the first communication we've had with this device, this is rubbish and we can don't worry about it for now. But that same process exists for frame 2. I've sent something here, this is the second byte I've sent, and now effectively this is the first useful byte that I've received from my slave. So I send something for only the purpose of receiving a byte back again. The slave cannot initiate a data transfer. Okay, cannot initiate data transfer. Alright, so this is the slave we're talking about here. Slave has to wait, even though I've said in this instruction here, I want you to tell me what voltage you've currently got in one of your pins. It has to wait until me as the master executes another data transfer. Alright, and I like to think of these as exchanges. I have an exchange between I give the slave a byte and the slave gives me a byte back again. Alright, so we have transfer here and here simultaneously, hence full duplex, at the same time, which then means we get both sent and received in one transfer. Remember though, in order to tell the slave device to do something, it's going to have to go across 2 frames. Alright? Sorry, to tell the device to do something and receive a reply, it goes across 2 frames. So for the first one, we sent it the instruction, and for the second one, we don't receive an instruction back, we receive our data back again. Alright? Send one to tell it what to do, send another one to receive the data back. So with SPI, you must always, if you want to receive something back again, you're going to have to send 2 transfers normally, unless you're doing something a little bit fancy. So that's the basic premise of SPI. 4 lines normally, full duplex operation, synchronized because we share a common clock line, and remembering this fact that we have to send something to receive something. Alright, every time you send data, you also receive data. But you cannot initiate data transfer without first sending something. Alright, so that's how SPI works. Let's look how we'd set it up. Now there's actually only realistically 1 control register that we have to worry about for SPI, which is another reason that makes it so nice. We've got interrupt enable, which is really useful if you want an interrupt to fire every time you receive a byte, for example. Not so useful if you're doing all the data transfer yourself. So not going to worry about that. SPI enable, absolutely, we're going to need that. Data order, you can customize whether you send the most significant bit or the least significant bit first. Alright, so that's important too. Normally, we're going to be doing most significant bit, but it changes. Master or slave select, only the master generates a clock, right, in the direction that that clock's going in. Alright, so if we don't set our microcontroller up as the master, nobody's going to generate the clock. So we're going to need that one. These two, CPOL and CPHA, I'm going to get to shortly. And these last 2 bits here are the prescaler. Just like we see in a timer. Now we actually have a range of frequencies here depending on this 2 times bit, which is actually located way down here in the status register. So normally status is for reading, in this case it's actually a writing register. So you can change that to give us a bit more changes in clock speed, but normally I work with these ones, and normally I'm here. Normally, slowest clock speed. Now the reason I do this is because normally there is no Fmin in the slave device. There is always an Fmax. So if you're running at the slowest possible, there's a good chance that you're going to be working alright. Alright, it's not going to have any problems. The other problem is, the faster you go, so if we're coming up to this one or even this one, alright, the chances of you running into problems with, if you've got a longer PCB tracks connecting the components, or you've got a lot of noise, or capacitance between those tracks, alright, you can start running into all sorts of problems. So normally, start slow. Once everything's working, okay, you've checked that you can receive and transmit bytes as you want to, then you can speed up. Then speed up as required. Alright, but that's optional. You can leave it going as slow as possible if that works for you. Alright, so normally, most significant bit, always, and I'm going to put that in quotes because very seldom you would actually want to work as a slave. Master, obviously we always must enable it if we want to use it, and sometimes we might be interested in using the interrupts. Right, so those ones are all nice and easy, and we can just select the bits as required. So normally this is the one we want here. Keep it nice and slow. Which leads us to these 2 bits here, which are unfortunately a little complicated. So we have actually 4 different modes, 4 different clock modes that we can operate in. Unfortunately, these SPI modes here from 0 to 3 a slave device from a certain manufacturer, their SPI mode 3 might actually be SPI mode 0 here. So you can't necessarily line those up, although generally it's a good place to start. So what we've got is, between those two bits, we've got the options of having rising and falling for leading and trailing edges. Alright, so this one is idle low, and this one is idle high. Now what do I mean by that? Okay, idle low, while this one is idle high. Alright, so some devices will expect falling edges as the leading edge, while rising edges for the trailing. So this is the leading, and that is the trailing. And some are expect, as we'd normally expect, rising leading and falling trailing. Right, so you've got to look at the data sheets to do that. We're going to have a look at the end, how to do that. But we also have clock phase. So this is clock polarity and this is clock phase. And what we can see down here in this particular timing diagram here is for CPHA is equal to 0 in this particular example, the leading edge samples and the trailing edge sets up. So let's have a look at this. The leading edge, which is always going to be this, no matter, which way it's going, okay, whether it's idle low or idle high, we're going to, on the leading edge sample, which is this part here, so we're sampling master in, and that's going to happen in the middle, hopefully, of where the data has been set up, and on the trailing edge set up. So on our trailing edge, which is here, we're going to set up the next bit coming out of our SPI port. The alternative, as we see here, is that we can actually sample on the trailing edge and set up on the leading edge. Alright, so we can flip those around. Depends on whether we want to sample on the leading edge or sample on the trailing. That's the easiest way I look at it, is the sampling, rather than worrying about the setup bit, which is a little bit more complicated. Right, there's, as far as I can see, no default here. Okay, there's a whole range of different devices, and you're just going to have to look at the data sheet. The C-pole, 0 is the most common. So that one you can normally safely assume is going to be alright. So that's our SPI port. That's the control register. The only other things that you need to be aware of now are the status register and the data register. Right, status register, we've got one bit here which is key to actually understanding whether checking whether it's correct, functioning correctly or not. You've actually received something. This one's actually the interrupt flag, but if you're not using interrupts, then this one's fine to use as well. You have to use it to check if the communication has succeeded. Alright, so when a serial transfer is complete, the SPIF flag is set. So you have sent some information, sent some data. You then need to wait until SPIF bit 7 equals 1, then you can read. Alright, so basically I've said at this time point, got a timeline here, this is where I'm going to send. Obviously it's going to take some finite period of time, it's not going to happen instantaneously. This is the sending and receiving time. Remembering that when we send a byte, as I said up here, every time you send data you also receive data. So at the same time as I'm sending, I'm also receiving. And then at this point here, SPIF will go equal to 1. Dot 7 will go equal to 1. Alright, so SPSR dot 7 and SPSR bit 7 will go equal to 1 there. So you need to wait for that, just like in a serial port where you have to wait until the a byte has been received. And at this point, now I can read the data. Alright, so this is our flag to check if, remember I've used that word exchange complete. That's the flag we're looking for. Alright, last thing we need to look at then is SPDR, which is our actual data register. Now this is our read and write register used for data transfer. So SPDR equals data. That will initiate a transfer, or as we called it, an exchange. Wait for SPSR bit 7 to be equal to 1. Okay, and then we can go RX data, so what we've received back, equals SPDR. So we see that this is transmitting and this is receiving, and it happens with the same register. That's quite critical. And remember, all we've received back is whatever the last set of data instruction was. If you haven't sent anything previously, then this will be rubbish. Right? And in order to receive back the information we're asking for in this data, we have to repeat this process again. But points to note, SPDR is for writing and reading, and it will contain the received byte after the communications has finished. So I thought what we'll do is have a look at an example where this all sort of comes together, and that's the real-time clock that we have on our applications board. Alright, so between all of this we're going to apply looking at first the control register and then how we might communicate with the device. So this serial real-time clock is the data sheets just on AUT Online. You can go through it as you like, but I've highlighted just the main sections in here. And we're going to have a look at the read command, because that's, I think, one of the first things you should do to see whether it's working or not, is to read something that you expect to be changing. In this case, note active high for the chip enable. Okay, that goes against the normal. Got clock, can be either polarity, so CPOL 0 or 1 is okay. That's a nice feature of this particular chip for us. Serial data in. Not all devices will use the same MOSI and MISO names. And serial data out. So we've got two different lines as we expect. This one is serial data out from the slave. So in this case this will be MISO, and this one will be MOSI. Slave data in, slave data out. Okay, or serial data out. So the first thing that happens is we send an 8-bit address, then send anything. Remember, it's just rubbish, in order to be able to receive our 8-bit data back again. So just like we had before, we've got 1 frame of data and 2 frames here. So 2 bytes are transferred in order to receive 2 byte transfer equals 1 byte received of useful data. Okay, we may have received something here, but not unless we had asked for something previously. If the slave device, and this time our real-time clock's not expecting anything, then that will be what we get there. We'd have a high impedance there. Looking at the serial clock as a function of clock polarity, as we saw before, we can use either clock polarity. However, the shift out on data read, so this one is CPOL 1, this is CPOL 0. Normally we'll be using this one. So that looks like the slave is is shifting out data on the rising edge and latching it or reading it on the trailing edge. So we come back up here. Latching it on the trailing edge means that it has to have been set up by then. So in this case, we come back to our table. Okay, it has to have been set up on the leading edge in order to be latched by the slave on the trailing edge, and correspondingly it sets up, shifts the data out on the rising edge, or the leading edge, sorry, of the slave, so we can then sample it on the trailing edge of the master. Right, they both can't happen at the same time. So in this case, we know that CPHA is equal to 1. It's a little bit confusing. I get this wrong a lot of the time. Thankfully, there's only 4 options. All else fails. Try all 4 options. Alright, you've only got CPOL and CPHA. If you can't work it out, try it with all 4 options until you get something working. I know it's not brilliant, but they are a little bit confusing to work out. The only other thing we need to think about is looking at the electrical characteristics of our SPI, and the important one here is our clock frequency. So at 5 volts, which I assume we're operating at, we can go right up to 2 megahertz. And you see the minimum, well, is DC. So right down to, well, 0 hertz effectively, although that wouldn't actually communicate any data. But however, alright, so there's no effective minimum frequency. We can go right up to 2 megahertz though. So let's look how we'd set this up based on what we've seen here. Alright, we can see things like 7 versus 0. So I'd assume that that's most significant bit first. So of our register, which is way up here, sorry, we're going to have to enable it. Data order, most significant bit, definitely master. CPOL can be either, but let's say we're going to make that 0, that 1, and we'll choose the bits associated here to give us the slowest corresponding clock speed. Alright, so this is going to look like for our real-time clock 0, 1, 0, 1, 0, 1, and I believe that was 1, 1, 1, 1. Alright, for our real-time clock. Alright, no interrupt, enabled, most significant bit first, operating as a master, idle low with the phase set up as per bit 1 and operating as slow as possible. Alright, so that would get at the communication, hopefully the hardware set up correctly to be able to communicate with it. The only thing we also need to now consider is the actual device itself and how we read and talk to that. Now, one of the most critical things is this delay here. And we actually see it here. You can't just go, for example, CE equals 1, SPDR equals data. Alright? Not going to work. Remember, our microcontroller might do this in, if you're really lucky, 125 nanoseconds at 8 megahertz. Alright? This time here, we can see between the chip enable going high and the first corresponding clock pulse, TCC actually has to be, worst case, 4 microseconds, which is a lot longer than the 125 nanoseconds we've got here. So there is usually a delay between SE equals 1 or 0, whatever it is, and SPDR equals data. So just watch out for that. That's quite common. The rest of these ones I don't believe we have to worry about because they are all with respect to the actual hardware port. So the SPI hardware controls it. But this one is under our control. So we have to watch out for that one. And we're going to show you how that will play into it further on. Looking at the internal registers of our real-time clock, we've got 2 important bits that we need to watch out for, as well as the table of functionality registers associated with this device. So just to quickly highlight this, quite often people will jump to, I just have to read address 00H to be able to get the seconds. Alright, And you'll do that, and you'll wait, and nothing will happen, you won't get anything back, and you wonder what's going on. Well, enable oscillator. This bit is set to logic 0, starts the oscillator. On application of power, this bit will be set to logic 1. It starts disabled. So it's no wonder, even though you've got all your SPI set up correctly and you're reading the right address and doing everything like that, first thing you do is you actually have to start the device. It doesn't start on by default. And in fact, before any write operation to the clock or RAM, there is a write protect bit. So the first thing you must do, so including bit 7, is actually write a 0 here. Then, just to be on the safe side, we should probably write a 0 to there again. Alright, so we need to be careful, look at the control registers, look at the startup sequence of this device, because commonly you won't find that you can go straight into it. You'll actually have to do some sort of control setup. So using this device might look like SPDR equals, we're going to send the address we want to be able to write to it, OX8F. Okay, so this is the address of the control register. We'll have our chip enable equals to 1, and we'll have a delay microseconds of, let's say, 10, just to be on the safe side. This is pseudocode, by the way. Wait for that SPIF flag, and then we can go, let's say, rubbish equals SPDR. So we should always read it back in to clear the flag. Alright, so that's sending the address. All that's done is tell our real-time clock that we want to write to this register. That's all it's done so far. We haven't actually written to it. Next, I normally have a small delay in here. It's up to you whether you do or not, but maybe 1 microsecond or something like that. We write to it again. SPDR equals OXOO. Now the reason we've chosen that is I want to make this bit 0. Alright. Therefore, this bit should be cleared before attempting to write to the device, so we're clearing it. So we're writing to that. We're actually making everything 0. Doesn't matter, but we are making that one definitely 0. Wait for the flag again. Read it back if you want to. Alright, so now at this point, write protect is disabled. Maybe a small delay again. SPDR equals OX8F. Wait. Rubbish equals SPDR. And that's the address sent again. And SPDR equals OXOO. Wait. Rubbish equals SPDR. And now at this point, finally, the oscillator has started. Right, so you see, it's actually quite a procedure, even though we're actually only writing to one register. And depending what you're going to do next, maybe you have you put the chip enable back to 0. Right, so we bring down we make active high, so we raise up the chip enable line, small delay to take into account this delay required here. We then send the address of the control register that we want to write to. So write is 8F. Don't worry about the H, it's hexadecimal. To read it would be 0F. We're not interested in reading it, we're interested in writing it. Send the address. And if you're interested, we can follow what we're doing here. We're sending the address. And then we send the instruction or the data that we want to. So in this case, we send the address of the register that we want to write to, which is done here. We then wait for that communication to be complete and we read back to clear the flag. It's always a good idea to read it. So the address is now sent. We are halfway along. We're at this point here now. In order to send the next 8 bits, we need another data transfer. So like I say, sometimes a small delay. we send all zeros as I described, wait for it to be complete, read back again. We've now disabled the bit. Alright, it's possible that the first write didn't allow us to actually write to this flag because that was protected. That's what the whole idea of that is. So we have to then ensure that stays 0 and actually now write a 0 to that. Starts the oscillator. So we repeat the process again, but instead of this time disabling the write protect, which we've already disabled, we now start the oscillator. And at this point, we could, for example, go SPDR, we'll do our C equals 1, our delay, microseconds 10. SPDR, if we want to read the seconds register, okay, you can see read 00, OXOO, wait, the SPIF. Obviously the first bit we get back is rubbish. Okay, we're doing a read operation now. Okay, so I've sent the address like I've done here. Everything that comes back we're not interested in because it hasn't got the required address yet. Now, once we've done that, we've got address sent, SPDR equals whatever. Okay, I'm just going to say rubbish here. Nothing to send. We don't care what we send. Okay, wait. And now we can say the seconds is equal to the information we would get back in SPDR. Right, so we've actually got information back. So we have now read the seconds register. Okay, so you can see there's quite a little bit there that's required in order for you to get a grasp of communicating with this device. At this point now you can send, for example, another address. Let's say you want to read the 10 minutes ones, where you could send 01 instead of 00 here, you'd send 01. And when you next read from the port again after sending a, what I call a dummy byte, you would receive back the contents of the minutes register inside that real-time clock. Alright, so things that we had to remember were looking at the datasheet for things like maximum speed, any delays that were required, how the clock phase was set up, and clock polarity, and whether it was sending it most significant bit first or least significant bit. But we could obtain that by just looking at the SPI port. Alright, I realise this is a long video, but hopefully that has given you a good introduction into SPI and how you could then use that with a common peripheral.